Hi, I am Demorny Baker. I'm a math instructor in Hartrust NTA, and today I want to showcase 10 hands-on manipulatives and 2 e-resources that can be used in the classroom to help students better understand math concepts. Now, I'll also be demonstrating how these tools work, some of the concepts that they can be used to teach, some of the challenges that you may encounter while using these tools, and ways how you can reduce some of these challenges or address some of these challenges. But before we get into the video, guys, let's first look at what are math manipulatives, right? Now, math manipulatives are described as concrete objects that allows students to explore math concepts using a hands-on and active approach. These objects can include blocks, shapes, cubes, money, counters, just to name a few. Now, while math manipulatives can be useful tools that can be used in the classroom, it is important to note that the tools themselves does not allow for better learning outcomes, but teachers must ensure that they have enough knowledge of these tools to use them effectively in the classroom, hence this video. Now, whilst we're going to look at 10 hands-on manipulatives, I'm going to go in depth with about 4 of the hands-on manipulative and 1 of the e-resources, right? So stick around, let us get right into the video. So I'm going to go in depth with the first 4, and number 1 on the list are paper, scissors, and pencil. You heard that right, guys. Paper, scissors, and pencil. Now, many times when we think of manipulatives, we limit our thinking to tools such as a Geoboard, Algebra tile, pattern blocks, fraction strips, etc. However, there's a lot that we can do with a sheet of paper, a scissors, and a pencil. Now, some of these concepts that can be developed or explored using these tools include the properties of shapes, the properties of solids, reflection and its properties, line of symmetry, and the one that we'll be looking at extensively in this video, triangle angle sum. That is proving that the sum of the interior angles in a triangle adds up to 180 degrees. And whilst we have listed 5 concepts that we could use these tools to teach, I'm sure if we think hard enough, there is possibly many more concepts that can be explored and developed using a paper, scissors, and pen. Alright? Now, how can we use these tools to actually explore triangle angle sum, proving that the sum of the interior angles of a triangle adds up to 180 degrees. Now, the first thing that we want to do before we go ahead with the activity is to ensure that our students have the prerequisite skills to be successful in this activity. And by successful, we mean that we want to ensure that they have the prerequisite skills that is needed to make appropriate conclusions based on what they will be doing. Now, some of these things include they should be able to identify a triangle. They should know what it is, how many angles makes up a triangle, etc. Now, they should also be able to identify the different types of angles, especially a straight line angle and a complete rotation. They should also know that a complete rotation measures 360 degrees. In addition to that, they should be able to recall that the angles at a point on a straight line adds up to 180 degrees. In addition to that, they should be familiar with terms such as vertex or vertices and angles. Now, what is the objective of this activity? We want the students to explore the sum of the interior angles of a triangle. Now, let us get into the activity. Now, the first thing that the teacher would want to do is to determine whether or not he or she will allow his or her students to actually carry out this activity in groups or individual, etc. Right? It's good if students work in groups. That will allow them to have discourse among themselves and may even increase the possibility of them making even better conclusion as it pertains to what they would have observed. Now, the first thing that we're going to do in this activity, the teacher will ask the students to draw a triangle on a sheet of paper and label all the interior angles, which means that you'll decide. I think it's best for the teacher to provide the students with these tools, a scissors. So if you don't have enough scissors, what you could do is to place the students in group, which will reduce the amount of scissors that you will be needing, right? So you can provide the students with scissors, the blank leaves or whatever leaves you'll be using, and of course they'll have their pencils. All right, now after asking the students to draw a triangle on the sheet of paper provided and label all the interior angles, the teacher could then ask the students to cut out the triangle that they have drawn. Right, so they're going to cut out the triangle out of the paper that they would have drawn, after which the teacher can ask the students to cut off each of the angles and place them together such that all three vertices meet together at the same point. Now, this step may lead to some confusion somewhat. The students may place all the vertices together, however they may not arrange it in such a way that allows for them to see the relationship between the angles and let's say the circle, so that the angles will maybe form a semicircle, or even that it forms angles at a point on a straight line, depending on how they arrange these angles. So the teacher is there as a facilitator to guide the students throughout this process. Now, whilst we have outlined the steps of how to carry out this activity, it helps to actually do some demonstration. So I'm going to do a demonstration now of what we expect our students to do throughout these the exploration activity. So let's get right into it. Now, the first thing that we want to ensure before we can proceed with the activity is to ensure the students have all the tools needed to successfully carry out this exploration activity. So they should have a sheet of paper, they should have a scissors, a straight edge, doesn't have to be a ruler but a straight edge, and of course a pencil. Now, first thing that I want the students to do is to draw a triangle of their choice. Of course, I'm going to draw a triangle. All right, there we go. Now, after drawing the triangle, we want them to identify the angles. So they could label them A, B, and C, for example, 1, 2, or 3. All right, so let's say A, B, C. All right, so we would have labeled the angles. Now, the next step is to actually cut out our triangle. Now that we have successfully cut out our triangle, the next step is to cut off our angles. So we could do so. I want to cut it off, don't want to do it too small. Alright, so there we go. Alright, so there we go. So we have successfully cut off our angles. Now the next step is to arrange these angles such that all the vertices meet at the same point. Now, this was a part that I was talking about. Some students may arrange all the vertices at the same point, but they may arrange it like this, right? However you want them to arrange it in such a way that they all combine to form one angle. Right, so there we go. See how best we can do that. So you want to guide the students throughout this process. So there we go. Now, once the students have reached this stage, then they would have pretty much carried out the activity. Now the teacher can proceed to start asking questions. You can ask the students, what have you observed here? Some students may say, that looks like a half a circle or a semicircle. Others may say, these are angles at a point and a straight line, etc. Some may give responses that may not be appropriate. However, we welcome the responses nonetheless. Now, what we want to do in addition to that is to ask follow-up questions, guided questions, so that that will aid the students to make appropriate conclusions. So for example, we could ask the students, what conclusions could be made based on what we are seeing here? What can we say about the angles? Recall that these angles were the same angles that were a part of the triangle. They all combined to make a semicircle or angles at a point and a straight line. And they may say, well, these angles add up to give you 180 degrees. Now, once they say that, if they draw that conclusion, the teacher could say, give reason for that conclusion. The students may say, a circle measures 360 degrees, therefore half of a circle would measure 180 degrees. The three angles combine to make half of a circle, so therefore the sum of the angles of the triangle adds up to give 180 degrees. Other students may say, well sir, or miss, all three angles form angles at a point. They are angles at a point on a straight line, and those add up to 180 degrees. So therefore, A plus B plus C is equal to 180. So the angles in the triangle add up to give 180 degrees, which is the conclusion that we want the students to make, right? So that's pretty much the activity, how you could use a paper, a scissors, and a pencil to explore triangle angle sum. Very effective, and it can allow for a better learning outcome. Just to integrate writing tasks in this activity, the teacher could ask the students to write down what they have observed, write down conclusions that they could actually make based on what they would have done. Right? They could also share it with the class, share it with their classmates, ask them not only while they will be sharing, you can give the students the opportunity to justify why they would have made those conclusions, all of which is good in the math classroom to allow the students. It promotes a student-centered classroom. The students would be the center of the learning process, and it allows them to draw their own conclusion, debate, make justification, and using guided questions, the teacher can get all of these out of the students. Now, the second manipulative that we'll be looking at in this video is an analog clock. An analog clock is a circular phased clock with the numbers 1 to 12 around the outside, and sometimes they have two hands, a short one to measure hours and a longer one to measure minutes. Some clocks even have a third hand to indicate seconds. In the math classroom, clocks are mainly used to tell time. Of course, once you hear the term clock, you associate that with time. However, there are other concepts that can be explored using an analog clock, such as fraction and angles, which is the concept that we'll be looking at more extensively, how we can actually use an analog clock and integrate an analog clock in the concept of angles to help students conceptualize what angles are all about. Now, before we get into it, let's just look at what an angle is. An angle can be defined as the amount of turn about a point. Angles are usually represented with the use of two rays which share the same vertex and a curved arrow that shows the degree of turn. However, rather than simply drawing this image to show an angle, an analog clock can be very effective in helping students making sense of what the concept is all about. Now, in addition to that, it can also be an effective way of clarifying a popular misconception students have as it pertains to angles. Many times the students are of the view that the longer the rays are, or the further up the ray the curved arrow is at, then the larger the angles are. However, that's not the case. As shown in the diagram here, both these angles are 45-degree angles. The size of the angle is not dependent on how high up the curved arrow is and how extended the rays are. It is dependent on the degree of turn. So the analog clock can be a very effective tool to reinforce the concept of angle, what it really is, and how do you determine the magnitude of an angle and also the type of angle. Now, prerequisite skills, of course, we want to ensure before we go into our activity that our students have the prerequisite skills needed to be successful in making appropriate conclusions. Now, some of the prerequisite skills that we expect students to have before going into the activity includes they should be able to identify the graduations on the analog clock, the hours and minutes. They should recognize that a complete rotation or revolution measures 360 degrees. They should also be able to define the different types of angles, such as acute, right, obtuse, straight angles, and reflex angles. So the objectives of this activity is to reinforce the definition of angles, identifying the different types of angles formed in the clock, determining the magnitude of the different types of angles formed in the clock. And now we're going to get straight in our activity, and just like the previous activity, I'm going to outline the activity, then we're going to do a demonstration to help us make sense of what it is all about. Now, the first thing that we want to do in our activity, we could start by placing the students in groups to help promote the students being the center of the learning experience. This is what it's all about, guys. We want the students to be the center of the learning experience, as this will allow the students to have discussion with their peers about their observations throughout the exploration activity. And as I would have mentioned in the previous activity, it may even increase the possibility of them making or drawing appropriate conclusions, because they have the chance of working together. They are discussing among themselves, trying to make sense of what they are doing. Now, next, we want to check for the prerequisite skills, of course. So we want to ask the students to make a complete revolution or rotation with the minutes hand, just to ensure that they understand what a complete rotation is all about. We expect that the students will, let's say, both the minutes hand and the hour hand is at the 12th hour. Then we expect that the students will rotate the minutes hand all the way around until it's right back on the 12th hour. That's how they'll actually demonstrate that complete rotation. Now, after which the facilitator can ask the students what is the degree of turn they just made. So we also want to know that the students understand that a complete rotation measures 360 degrees. They can build on that knowledge to determine other angles that will be formed later on in the activity. After this, the teacher can then ask the students to place both the hour and minutes hand at another hour of their choice. So you don't just want them to be using the 12th hour of the day, you want them to move around the clock. They could maybe start both hands could be on the second hour of the day. All right, And from there, the students could turn, let's say, 6 hours from there, so they'll end up at the 8th hour. After which, the teacher could ask the students to determine or identify or state the type of angle that is formed after doing that, and the magnitude or size of that angle that is formed. Now, as you can see, there is a good activity. Students can carry out calculations. Of course, they'll be manipulating the clock. They can visualize what they are doing. Now, during this activity, the teacher wants to seize the opportunity to reinforce that the magnitude of an angle is dependent on the degree of turn, right? It's dependent on the degree of turn and not based on the length of the ray or how far up, if I can put it like that, the curved arrow is that represent the angle that is formed. So you want to seize the opportunity. The analog clock is a perfect tool to use to help students conceptualize that the size of the angle is dependent on the amount of turn that is taking place. So they'll see that while turning the minute's hand, the more they turn it, the greater, the more they turn it from the initial point where it was, the greater the angle become. All right, now let's get right into the activity. So we're going to do a demonstration on how we could actually help students to do this. Now here we have our analog clock, and on this clock I actually incorporated a seconds hand. However, because we're going to use this for the concept of angles, then we could remove the second hand. Not that it couldn't remain, but we don't want to make it too confusing for the students, so we want to limit the number of hands that is on the clock, especially when we're just starting to introduce the students to the whole idea of angles. All right, so we remove the second hand and we'll be using the hour and the seconds hand here. Now, what we could possibly do is to start with both hands pointing at the 12th hour. Now we could ask the students to rotate, make one complete rotation or revolution with the minutes hand. So we expect the students to go all the way around with this one, all the way around until they come back to the point that they would have started. Right? After the students would have done that, the teacher could ask the students what is the degree of turn that they would have just made. And of course, we're testing for the prerequisite skills here, so we expect the students to say that the degree of turn was 360 degrees. Of course, in addition to what we are saying here, the language that we use in the math classroom is very important, so we want to ensure that we use the correct math language so that it makes it easier for the students to conceptualize the concepts that we are exploring in the math classroom. Now, note that the students will be in group while they are doing this, so they'll be able to have discourse among themselves. They could correct each other, make suggestions, and develop their own understanding based on the discussions that they are having among themselves, right? Because we always want to have a student-centered classroom, because we want our students to be as independent as possible. We want to promote independent learning. All right, now in addition to that, we can start, as we said, in the activity. It doesn't have to be the second hour, but you get the whole idea. We could go to the second hour and ask the students to rotate. So from here, 6 hours away, so we have, this is 1 hour, 2, 3, 4, 5, 6. For the students to do this effectively, they must have some knowledge of time as well. It's very important that they have knowledge of time, and as I mentioned before in the prerequisite skill, they must understand the graduation and the clock and what they represent. Now, the students may just look at it and see that a straight angle would have formed. So you can ask the students to identify, of course, the angle that is formed, the type of angle that is formed. They may say the straight angle. You can ask the students what is the size of the angle, and they may be able to say that it is 180 degrees. Now, the teacher, you don't just want to take the responses of the students like that. You always want the students to justify their response. So you can ask them, why is it a straight angle? And the students may say it looks like a straight angle. Some may say the reason why it's a straight angle is because it measures exactly 180 degrees, which is the ideal response that you will be looking for. In addition to that, you want to ask the students after even if they have determined the correct size of the angle, you can ask them, how did they conclude or determine that the angle is 180 degrees. Now that brings us back to the first thing that would have allowed them to do. Then if the students know that rotating all the way around the clock back to the initial point where they would have started from is 360 degrees, then you want them to give them the challenge to figure out and ask them if they have struggle, that is to figure out the degree. You can ask them, how much degree would you have to turn in order to move from 1 hour to the next, right? So hopefully the students can build on the knowledge that they have of number sense and number concepts, and understand especially the operation of division here. Understand that here we have 12 hours. If rotating all the way around, we have rotated through 12 hours, and a complete rotation is measures 360 degrees. So if we have 12 hours and we should share 360 degrees equally among these 12 hours, then each hour would, to move from 1 hour to the next, would be 30 degrees. So we want the students to be able to do these types of things. Maybe at the initial point you don't want to go to the point that they know how much minutes they'll have to move from 1 minute to the next. May not want to go to that point as yet. However, you can build on that in future lessons, of course. Now, you can ask the students how they got the 30 degrees. They should be able to see that if you share 360 equally among the 12 hours, then it would have been 30 degrees. So the operation there would have been division. 360 divided by 12 is 30. All right, so those are a few things that we could do, and you can allow them to make angles of their choice. So they could have a starting point, turn through any amount of hours that they want, they could see. And it's good to reinforce even the types of angles here, and the importance of actually showing the turn that is taking place, where the turn is taking place. For example, it can reinforce why we have graphical representation using the raise and the curved arrow to show where the turn is taking place. Because if they turn from this point all the way around to this point, then they would have formed a reflex angle based on the turn. They'll be able to know that, well, this turn is greater than 180 degrees, but it's less than 300 degrees, so it's a reflex angle based on where the turn is taking place, right? So they wouldn't just look at this part and say, oh, it's an obtuse angle, right? Based on the turn, where the turn is taking place, then they'll know that this is a reflex angle. However, if the turn was, let's say, like this, then it would have been a obtuse angle. So it's based on where the turn is taking place. So it's very important when doing graphical representation to show with the curved arrow where the turn is taking place and the degree of turn that is taking place. All right, hopefully I didn't leave anything out. So that's pretty much how we can use the analog clock to develop and explore the concept of angles and reinforce the definition of angles, and to reduce the misconception that students have as it pertains to so in addition to that, teachers should seize the opportunity to reinforce that the size of an angle is dependent on the degree of turn and not how far up the curved arrow is, or how or the length of the rays. All right, when doing graphical representation, so they can make sense of it that it's the degree of turn based on using the clock. All right, so now let us look at our third set of manipulatives. We have the cylinder and a cone with the same dimensions. Now, a cylinder and a cone with the same dimension provides students with an excellent way or opportunity to actually explore the relationship between the volume of a cylinder and a cone with the same dimension, how they relate to each other, and be able to derive formulas, the formula of the volume of a cone, of course. Right, so first thing first, of course, just like any activity, we want to ensure that our students have the prerequisite skills required to be successful at making appropriate conclusions throughout the activity. So one of these prerequisite skills that is essential, students should be able to recite the formula of the volume of a cylinder. So they must already have knowledge of the volume of a cylinder, and because that's pretty much we need to know that in order to derive the volume of the cone. So we must have knowledge of the volume of a cylinder and the formula that can be used to ascertain the volume of a cylinder. Now let's get right into our activity. Now the first thing that we want to do is to ensure that our students have the tools required to carry out this exploration activity. In addition to that, we want to ensure that we decide whether or not the students will be carrying out this activity individually or in groups. We want to promote the group activities because it allows for a student-centered classroom, allow the students to have discourse among themselves, and as I always say, it may even increase the chances of them drawing appropriate conclusion or making appropriate conclusion. Now let's say, for example, we allow this activity to take place in a group setting. So we have the students in group. The teacher could ask the students to fill the cone with salt. So we're also going to provide the students with salt, of course. You need salt depending on the material that the three-dimensional figures or objects are made out of. Then you can use possibly liquid. The one that we'll be demonstrating in this video is made from cartridge paper. Alright, so we couldn't use liquid with this one, but you can use salt, sugar, sand, stuff like that. Alright, so in this exercise we can provide the students with salt. So we'll ask them to fill the cone with salt and then pour it into the cylinder, and ask them to repeat this until the cylinder is completely filled. Right, after doing this, the teacher could ask the students in their groups to write down the significant observations that they would have made throughout this exercise. What did they observe? What happened? What are some of the things that they can conclude based on what happened? Right, so in addition to that, and again, want to emphasize that both the cone and the cylinder must have the same dimensions for this to actually be true. All right, so let us demonstrate this as with the other manipulatives before this one, so we can get a better understanding or see what we expect the students to do and how they'll actually make these conclusions. So let's get right into it. All right, so now we have our manipulatives. We have the cylinder here and the cone, and both of them are of the same dimension. May not be easy to see on the camera here, but they're of the same dimensions, or pretty close at least. So I made these from cartridge paper. All right, so as I said before, we want the students to fill the cone. So I have a bottle here with salt, so we're going to fill the cone. Then we want them to pour it out in the cylinder, and we're going to repeat this until cylinder is completely filled. So as we see here, it took actually took 3 cones to completely fill the cylinder. So we want to emphasize that the bases of the cone must be the same, and the perpendicular height of the cone must be the same as the cylinder, right? So from this activity, the students can visualize and see that, well, it takes 3 cones of the same dimension of the cylinder to fill that cylinder, to completely fill that cylinder, right? And then they can make appropriate conclusions and determine that, well, since that's a relationship, then the volume of a cone would be equal to 1/3 of the volume of the cylinder. Therefore, if the volume of a cylinder is equal to pi r squared h, where r is the radius of the circle and h is the height of the cylinder, then the volume of a cone is equal to 1/3 of pi r squared h. And again, r there would be the radius of the circle, and h there would be the perpendicular height of the cone. All right, so there we go. That's how they could carry out this activity, and it's pretty short, brief activity, and it can really help students make sense of the formula of the cone. Now the 4th set of manipulative that we'll be looking at is the circle and string. Now the circle and string can be used to explore the relationship between the diameter of any circle and its circumference, which is what the value of pi is all about. In addition, the observation from this experiment can help students derive the formula of the circumference of a circle. It will help them to derive that the formula for the circumference of a circle is equal to pi times its diameter, right? And pretty much this is mainly what the circle and string is used for. Before we get into the activity, so you want to ensure that the students have the prerequisites necessary for them to benefit fully from the exploration activity. And the prerequisite skill that we want our students to have here is that they should be able to correctly identify the different parts of a circle, especially the diameter and the circumference. All right, now the teacher can then provide each students with the model of a circle of different radii, right? So we don't want the students to have circles of the same radius or with the same circumference. We want them to have circles with varying radii. So we want them to understand, we want them to use different size circles. That way the conclusion that is made, they can realize, oh, this conclusion, it works for any circle, irrespective of how large or small that circle is. The circumference of any circle is always 3 1/7 times its diameter, right? So you always want to do that. So that's something that you want to ensure. You don't want everybody to have the same size circle. You want them to use circle of different size. So this one is a little bit smaller than this one, right? and you can have them of varying size just to ensure that reinforce that it doesn't matter the size of the circle, this holds true for all circles, right? After which the teacher can ask the students to measure the diameter of their circles using a string, right? And it helps after they would have measured the diameter of their circle with a string, cut the string to the length of the diameter of the circle, right? It may be easier to use that way. I found it easier to use that way. Don't know what you think. Now after this, the teacher could then ask the students themselves to actually use a string to measure the circumference of the circle. In that, the teacher wants to ask the students to actually determine how many times can the string that they would have cut actually go around the circumference, right? So I'm going to do a demonstration of this so we can get a better understanding of what we expect our students to do and how they'll actually carry out this activity. So let's get right into it. Now here we are with our circle, and again you want them to do this with multiple circles, but I'm going to demonstrate this with one circle. All right, and as you can see, we would have already cut the string to the length of the diameter. All right, so what we want to do, so the first thing first, you had to ask the students to give them a string, ensure that they use a string. The string is the same length as the diameter, so they can give them a longer length of string and ask them to cut it to the length of the diameter. Or you could just cut the string to the length of the diameter of the circle and ask them to measure the diameter. They will see that the string is the same measurement of the diameter, and then ask them to see how many times can the string go all the way around the circumference. So in using this, right, they may want to have a pencil to actually mark how far around the circle goes. So for example here, ensure that that is in the camera. So here we are about there. And the thing about this exercise, it may not be 100% accurate, you know, but it will give the students a general idea of what expected. So I want to measure both these because of human error, of course. And have some challenges with the accuracy 100% there, but it will be pretty close to the true value of pi. Alright, if we do it precise enough. So here we go. So we mark those points, and from one of the points that we mark, string is here and up here, but we'll go around. So about here, so you realize that the string is the length of the diameter, and it actually goes around the circumference of the circle 3 times, and it actually left a little was left over, right? So what we can do, we can ask the students to actually measure the length of the string, of course, and record it. After which we could then ask the students to, let's say, actually use a string to measure the part that was left over, and probably mark that part of the string, mark that part with something. Alright, there we go. And then we could use a meter rule to actually measure this, right? So we can determine, of course, that what is left over is 2. If we want to represent what is left over as a fraction, it represents 2 centimeter of the 14 centimeter, which is the length of the string. Of course, we can reduce this by finding the highest common factor for both the numerator and denominator, which is 2. We know 2 divided by 2 is 1, and 14 divided by 2 is 7. So this is 1/7, right? So therefore, and remember what the string represents. The string was equal in length to the diameter, right? Therefore, what this is saying, if you took 3 1/7 string, irrespective of the measurement of what the string was, to actually completely go around the circumference, it means the same as saying here what? It's 3 1/7. Takes 3 1/7 of the length of the diameter to go all the way around the circumference, right? And it makes sense, right? Therefore, the circumference would be equal to this. Now, this 3 1/7, we have a special symbol for this value, which is pi. So therefore, we can say the circumference of a circle is equal to pi times the diameter of the circle, and the diameter, we denote the diameter using the letter D. So therefore, all of these can come out using the manipulative of the string and the circle. But again, may I remind you that it's very important that you not only do this with one size circle, but for the sake of time, I only demonstrated using one size circle, right? But you want the students to use different size circle to show that the relationship is always the same. In addition to that, sometimes they won't get the exact 3 1/7, but they'll get something pretty close. So that's one thing that may occur during this exploration activity, and that will actually happen because of human error. So if the measurement is not completely accurate, then the value of pi will not be completely accurate, right? So from this, the teacher of course can ask the students questions. You always want to do that and give them the opportunity to justify their answers. So from doing so, whilst I would have demonstrated all these working out and all of that, you always want to allow the students to do this, use guided questions to help them to make appropriate conclusions. So for example, after doing the measurement and realizing that it will take 3 1/7 of the string to actually completely go around the circumference of the circle, you can ask a student what conclusion can be made from this. So they'll tell you that relationship between hopefully they'll tell you this, that the relationship between the circumference and the diameter of any circle, right? After doing this with several circles, you want to allow them to do this with several circles and see the relationship being constant. It's the same relationship irrespective of the size circle. Then they can conclude that the relationship between the circumference and the diameter of any circle is that the circumference is 3 1/7 times the diameter of the circle. All right, so, and you can always ask the students to give reasoning for why they would have made those conclusions, etc. All right, now the fifth manipulative in our list here is the Geoboard, right? And what is the Geoboard? A Geoboard is a mathematical manipulative used to explore basic concepts in plane geometry, such as perimeter, area, and the characteristics of triangles and other polygons. It consists of a physical board and a certain number of nails or thumbtacks. In my case, it was thumbtacks, so I actually included thumbtacks in that. But oftentimes they build them using nails, right? And these are driven in the board, same units apart, right? and we can use those. We can wrap elastic bands around those to form shapes, and we can do many nice things with those, right? Now, some of the concepts that can be explored using the Geoboard include plane shapes, fractions, transformation. It can be used for counting, can use to form angles such as right angle, acute angle, etc. We can use it to form patterns, classification of shapes, perimeter and area, of course, which was already outlined previously. Now, we won't do an extensive demonstration on this one. As I said in the initial stages of the video, we're only going to look in detail at the first 4 manipulatives, which we have done already. However, I'll do a brief demonstration of how you could use the Geoboard. So let's get right into it. So loads of stuff that we can do with it, but as I mentioned before, we won't look extensively at this one. Right, so just did a brief demonstration there so you can get an idea of how you can use it. So you can play around with this and it can be used to develop and explore several math concepts. Now, 6th on our list is the Abacus, right? And an abacus is a calculation tool used by sliding counters along rod or grooves to perform mathematical functions. In addition to calculating the basic functions of addition, subtraction, multiplication, and division, the abacus can be used for counting and calculate roots up to the cubic degree. Furthermore, the abacus is also a very effective tool to allow students to make sense of the concept of place value, right? Now, again, we won't look extensively on how this thing, the abacus, can be used to develop a concept, but we will do brief demonstration of how it can be integrated in the math classroom. All right, and this is my abacus, and we'll be looking at how we can use this in the math classroom. So let's get right into it. Now, just to explain how the abacus works, the abacus is cleared when none of the counters are touching this middle rod right here, right? Now, the counters here, the first counters to our right, represent ones. So if I should count to 5, I would say 1, 2, 3, 4, 5. All right. Now, the counters above that one represents 5. So this represents 5, this represents another 5, so they combine to give us 10. Now, to the left of that one, the value of each of these is 10. So the place value, so let's go to the next place value. So this is, each of these represent 10, so that's 10, 20, 30, 40, 50, right? And each of these represent 50. So as you can see, the relationship here is that the beads above the ones below, they have the same value as all the beads below combined. All right, so this one is 50, and you get the pattern. These represent hundreds, so 100, 200, 300, 400, 500, and each of these beads represent 500. All right, and that's the relationship, and that's how you use the abacus in the basic sense. One demonstration, all right, before we move on to the next manipulative. let's say we want to count to 15, right? So we can ask the students to have 2 columns, 1s and 10s, right? So we can ask the students to count to 15 using the abacus, right? So they'll say 1, 2, 3, 4, 5, right? I want to go to 6, however I use up all the counters here. So what I'm going to do, I'm going to replace these 5 counters, right, with one of these which represent 5, and I can push this back down, right? So I only have 5 now, and I can say 6, 7, 8, 9, 10, and again I can substitute these 5 ones for a 5, right, and place them back here. So in total I have 10, right? Now I know that each of these counters represent 10, so I can replace these 2 5 with a 10. So now I have 10 here, 11, 12, 13, 14, 15, right? So I've counted to 50. So what you can ask the students to do is to write how many ones is in the number 15, right? And they realize, well, we have 1, 2, 3, 4, 5 ones, and we have 1 10, right? And that's pretty much how you write the number 15. It has 1 10 and 5 ones. So it does help students to make sense of place values, and as I said before, initial stages of the video, it can also be used for multiplication, division, subtraction, and addition, of course, right, which you can explore. Now let us move on to our next manipulative on the list. Now the 7th manipulative that is on our list here is what I call the area and meter rule. As the name suggests, this is a very useful tool to measure area and length, even perimeter, etc. Right? It can also be employed to ascertain the volume of a solid, right, or a 3-dimensional shape. Now the base of the instrument is designed in such a way so that it can be used to measure the area of the cross-section of a solid, and also allow for the measurement of the height or length of the object to be taken, right? So it's a very effective tool. This is it right here, right? So it has the base here, and I won't do any deep exploration on this one, right? So the base is made of graph paper, right, taped on with clear tape, a clear plastic and clear tape, right? And here we have this is not actually a meter, it's printed. It's a printed ruler, right, printed on paper, but the measurement is the same, is accurate, right? So that's pretty much what it's all about. So you can see we can use this to get the measure the area, right? For example, just go across and get this. So we could measure the surface area of this cuboid here. Can count how many units, can outline it, count how many units it occupies on the instrument here, and then we can also measure the height on the instrument, right? And once, if students understand the whole idea that the volume of a solid, which cross-section is congruent to, is equal to the area of its cross-section times its height, then we can use the instrument, record the area of the cross-section, record the height, and if we multiply those together, then it will actually give us the volume of that solid. All right, so that's one way how we could use what I call the area and meter rule, right? Now let us move on to the next thing in our list, which are counters, right? Very effective, may look a bit basic, but it's a very useful tool that can be employed in the classroom to allow for better learning outcome, right? Now, once students have mastered counting and identifying numbers, you can use counters to help teach skills such as addition, subtraction, multiplication, and division. Counters are a set of small circles. In my case, right, it's a set of small circles that can be used to explore the 4 basic operations among other concepts, right? In my cases, they are small circles. It doesn't have to be small circles, but I have small circles here, and I'll do a brief demonstration of how we could possibly use this for multiplication and maybe a few others. All right, so let's get right into it. Now here we have our counters, and what we want to do, we said we want to add 7 plus 5. We can color code the 7, right? So we're going to use a yellow for the 7, right? So we're going to use yellow counters for the number 7. So once the students can count, they know we have 1, 2, 3, 4, 5, 6, 7, right? So we have 7 right here. Now we add in 5, right? So we could use the red counters, right, for the 5. So we have 1, 2, 3, 4, 5, right? 5. So we have 5 here, and we have 7. So we're going to add them together. So all the students will be required to do is to count up how many counters they would have in total. So for example, you can say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Therefore 7 plus 5 is 12, right? So as you can see there, it's very easy to use. However, right, that the types of numbers that will be used with these manipulative must be fairly small numbers, right? And you must bear in mind the number of counters that we have in our possession. Now, what else can we do? We could use it for multiplication. Let's say we want to multiply 3 times 4. 3 times 4, and this will help students conceptualize what multiplication is all about. So 3 times 4 means that we have 3 sets of 4s. So we have 1, 2, 3, 4. That's one set. We have another set, 1, 2, 3, 4. That's 2 sets, and we want 3 sets because it's 3 times 4. So we want another set of 4. And then we want to count up how many counters do we have in total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Which means 3 4s is 12. This can also be used to multiply a positive by a negative number, as well as division and so many other things, right? So let's do it for subtraction and division, and then we can move on to the other manipulative. So let's say we have let's do division, right? Let's say we want to find out what is 6 divided by 2, right? So 6 divided by 2. So first we need 6 counters. And because we're going to divide them into 2, right, we're going to divide them into 2 groups. I want to ensure that both groups have the same amount, right? So we're going to divide them so that one that way, one that way. Ensure that both groups have the same amount of counters, right? So if we divide 6 by 2, we'll end up with 3 counters. Each group will have 3 counters, which means 6 divided by 2 is 3. And for subtraction, this is very easy. If we want to do, let's say for argument's sake, 7 minus 2, we'll have 7 counters, right? 7 counters. And if you want to minus 2, you simply just remove 2 counters from that and see how much counter will be remain. And as you can see here, would have 1, 2, 3, 4, 5 counters, right? So those are some brief demonstration on how the counters can be used in the math classroom. Now let us move on to our 9th manipulative on the list. Now our 9th manipulative on the list are colored match sticks, right? And I created these one from matchsticks, of course, and use a marker to actually color code them. So these are matchsticks. So these can be effective, a very effective tool to explore growing patterns, right? It can also be used for concepts such as addition, subtraction, multiplication, and division, of course, right? And I'm going to demonstrate briefly how you could possibly use this for growing pattern. How it is used for addition and subtraction is similar to how we demonstrated how to use the counters previously, right? So we're just going to look at how we can use this for growing patterns. Now, to use the sticks for growing patterns, what we could do is create maybe the first 3 patterns for the students. Right, so we can do that and then ask the students to actually create the 4th shape, right? So can start off with these before we start looking at a pattern in an abstract sense, right? Students may build the 4-1 like this. Alright, and from this activity, what we could probably do with the students is to ask them how many sticks would be required to build, let's say, the fifth pattern, right? Depending on the grade level students that we are teaching, right? If they have the ability, then you can ask them how many sticks would be required to make n pattern, right? Which means they must be able to determine the general rule that is going on here, so they can figure out a pattern, right? So they can write out how many sticks was in the first pattern, how many is in the second. So they will see that we have 3 sticks in the first, we have 5 in the second, 7 in the third, 9 in the 4th one, which means the one following will be 11. So they can see that the pattern is increasing by 2 sticks, right? And from that, we can make a whole lot of don't want to use the term predictions because it will be accurate. So we can determine how many sticks would be required to make n shape, right? The nth shape. So these are some ways how you can employ the sticks. As I said before, you can see it can be a very effective tool for addition as well, and you use it similar to because they are color coded, red and blue. Let's say you want to add 5 just to do a brief demonstration, and 2, then you can use one set of colors for one number and another set of color for the other, just so the students can distinguish between both numbers. Then add them up together and you'll get the sum of both numbers. So those are some brief demonstration of how the match stick can be employed in the math classroom. Now let's go on to our 10th manipulative. Now 10th on our list we have a dice and a coin, and both of these manipulatives can be used to explore the concept of probability, right? So this one was created out of cardboard and cartridge paper, right? So you can allow the students to conduct experiments using the dice, and you can do the same thing with the coins as well and ask them to determine the probability and all those nice stuff. So there's not many concepts that you'll use this for. You'd have seen me actually use this same the reason why I created it at this size, because I wanted to use it for the instrument that I refer to as the ear and meter rule as well, right? Just to demonstrate how we could actually use the instrument to determine the volume of a solid, right? So you can use this for probability. You can roll the dice and see how it works, right? And see what's the probability of getting a head or a tail, and see, do it, and compare the probability, being that probability is the desired result, divided by the total possible outcome. Then they can conduct experiment to see how close that prediction can be. The same thing can be done with the dice, right? Same thing can be done with this. Alright, conduct experiments and all of that to get a better understanding. That probability does not mean that this will definitely happen. It speaks to the chance, of course. So these two were the 10 manipulatives on the list. Alright guys, that brings us to the end of this video. So we would have looked at our 10 hands-on manipulatives and how we look extensively at how some of them could be used to develop certain math concepts, questions that could be asked, and just hints of how you can effectively use some of these tools in the mathematics classroom. So that brings us to the end of our video, everyone. I hope you found this video informative. I hope teachers benefit from this video and it gives you hints of how you could actually use these tools in the math classroom to help your students develop a better understanding of the math concepts that you are imparting in the classroom. Don't forget to subscribe to the channel if you haven't done it. Hit that subscribe button, hit the notification bell, and give this video a thumbs up. Share it with your fellow teachers, right? So we can get the message around, so that we can help develop and create better students of mathematics and promote better learning outcomes in the math classroom. I'm your host, Chris, from the Chris Maths Academy. Until next time, blessings and peace.